All right, so in this video, we're moving on to one variable equations in algebra. All right, so we're in Unit 3 now. We'll focus initially on Egyptian false position, and then we'll get into the other methods, Chinese double guess, Hindu inversion, and modern one variable equations. So you could read through this introduction. It gives you a little bit of a kind of a background on where these concepts came from and also how it ties together with other forms of algebra. All right, so have a look at that. But we'll move right into the one variable equations. Again, focusing on the Egyptian rule of false position. All right, so an equation takes the form of some left-hand side equal to some right-hand side. There's a variety of different ways in which you could write an equation. We're going to focus on the linear cases initially. One variable equation, so linear among them. But for example, 2 equals 1 plus 1 is an equation. All right, we have a left-hand side, we have a right-hand side, and there is an equality between them. All right. When you have something that involves a variable, so 2 equals 1 plus what, then this is an equation that will be true under certain circumstances, depending on what I put in the box. All right. For short, we tend to write this as something like 2 equals 1 plus x, but you could also look at it, if you didn't want to use the variable x, you could also look at it as 2 minus 1 equals box. All right, that's where the idea of subtracting from both sides of an equation comes from, or adding or multiplying or dividing. All right, the idea is that if I want to know what this is, I would want to know how the 2 and the 1 would need to relate to one another. All right, so if I'm trying to determine two values that'll add to a number, one way I can do it would be to say, all right, and I could use ages, for example. That's pretty common practice. So if I were to say my age and my brother's age add to 22, and I'm 10 years old, right? One way that you can do that would be to count up from 10 to 22. The other way to do it would be to say, okay, well, what's left out of the 22 that's available? I've already accounted for 10. So I would remove 10 from the 22, and that would arrive at the 12. You can just kind of reason it out, all right? But algebra kind of takes on its sort of a life of its own, because one, the equations aren't always that straightforward and simple, and the other is that you tend to go with symbolic notation rather than just kind of talking it out, right? Let x equal the age of one brother. Let this equal that, like the cost of admission to a carnival or something like that. All right. So the Egyptian rule of false position, I can read the preamble here. Many of the problems in the Rhine and Moscow papyri, right, papyrus plural, show their practical origin by dealing with questions regarding the strength of bread and beer, with feed mixture for cattle and domestic fowl, and with the storage of grain. Many of these require nothing more than simple linear equations, and generally solved by the method known as the rule of false position, because they did not let x equal the amount of grain, right? So they kind of thought of it differently, but arrived at basically the same concepts. So the first step really in any kind of word problem, we call them application questions, but they're essentially word problems. Translate the given problem into an equation, right? This is the part that can be a little kind of tricky to understand, but what you do is you guess a convenient value of x, right? Not necessarily the correct value, the emphasis on the guess, right? So you're going to choose a convenient value for x, but you don't really have any idea of whether it's the correct answer. You're just going to go with something that works nicely with the equation that you're given, right? You substitute it in, hopefully the value that you selected will eliminate any fractions if there are any fractions, right? By substituting that guess into the equation, you'll get most likely an incorrect answer. If you luck into the right one, great, right? But then from that, assuming that the value that you guessed was incorrect, we would come up with what we call the correction ratio, which is the given result, the value that you're aiming for, divided by your incorrect answer, right? So to get the correct solution, you multiply C by the guess. So X equals whatever that C value is, that correction ratio by your guess, and that'll give you the solution, right? So I'll run you through the example here. I'll actually, I'll guess a different number because, there's a printed solution here. So I'm gonna guess. Now, when I say a good value or where did I write it here? Would eliminate any fractions if present, right? So that would be a good guess. Obviously, some guesses are better than others, but anything that's a multiple of 7 would do that. So I'm going to guess X equals 2. I'm sorry, 14. The idea being that I wanted this to result in a 2, all right? The printed example used 7 because 7 divided by 7 is 1. So some number divided by 7 that would give you a clean number, so you don't have to work with fractions. This technique would work even if you didn't choose a good value, but obviously the computation would be a little bit more complicated, right? So if I do that, I get 14 plus 14 over 7. So 14 plus 2 is going to be equal to 16, all right? That would be the given result, the value that we came up with. I'm sorry, the given result is the value on the right. Your incorrect answer is the value we came up with, so that's the bottom, right? So C is going to be equal to 24 over 16. So that 24 over 16 I can reduce, right? It's not as clean as the example that was selected, so we're just going to go with it. But if I reduce this down, top and bottom are divisible by 8, which gets you 3 over 2. So 3 over 2 is my C, all right? So my answer X is going to be equal to whatever that correction factor is, correction ratio, multiplied by the guess. All right, so it's going to be 3 over 2 multiplied by 14, which is going to ultimately end up being a clean number. So 2 goes into 14 7 times. 3, that's already there, is going to be equal to 21. So my answer X is going to be equal to 21. They chose, in the example, they chose an X value of 7. I could have gone, if I wanted to, I could let X equal 1. It's just I'm going to be working with fractions, so if you want to try to avoid that, you might select something cleaner. But if you're in the right neighborhood of the correct answer, then you really can't go wrong. But sometimes you go into a problem not knowing what that neighborhood is. Contextually, in this problem, let's see. No, it just said solve for X, so I don't know the context behind it. If I were to say, unless it's written here somewhere, but if I were to say that X represents the amount of time it took to, prepare a meal, then I'd want to stay away from negative numbers. And, obviously if the time is in hours and I'm telling you that I'm preparing a meal, you shouldn't get something absurdly high, like 300 hours, right? You'd be preparing probably lots of meals over that period of time, right? You could also be given the context, in this case, example 2, a quantity added to a quarter of that quantity becomes 15. So it would make sense that that quantity would be some sort of countable value, right? A number of items. So I'm expecting X to, at a minimum, be positive, but I'm also thinking it's probably going to be a whole number, right? Something greater than 0, though. All right, so looking at this example, again, it's x plus 1/4 of x. So you choose a value that's convenient. They chose 4, which is the most convenient. I'm going to choose, I'll just do what I did before. I'll choose 8. So I'll say guess x equals 8. So we get 8 plus 8 over 4, but I'll write it the way they wrote it. 1 over 4 times 8, which is 8 plus 2, which is 10. All right, my correction factor or ratio is going to be what it should have been divided by what I got. Simplifies down to 3 over 2. Not always going to be the case, but 2 problems in a row, I got a correction factor of 3 over 2. Kind of makes it seem that way, but it's not. All right, my answer is going to be, so x is equal to the correction ratio multiplied by what I got when I made my guess. So I get a result. Oh, sorry, my guess was 8, not what I got, what the actual guess was, because we are solving for x. So we're looking at 12. Looks like 12. Oh, yeah, there it is. I didn't want to cheat and look down, but it was right in front of my face. I probably could have just looked. All right. So example 3, this one came right out of the Rhine Papyrus. A quantity, it's 2/3, it's 1/2, and it's 1/4 is added to become 145. So the translation of this problem is that quantity we call x, it's 2/3, so 2/3 of x. So 2/3 of x, 1/3 of x, or 1/2 of x, 1/4 of x is added and becomes 145. So when we say of means multiplication. So the quantity in its entirety, so all of it, so 1 of that quantity, so 1 times x, 2/3 times x, 1/2 times x, and 1/4 times x all adds to equal 145, right? The challenge here is to come up with that convenient value. And you can sort of reason it out, but it might not be the easiest thing in the world to come up with. If you want, you can just put it in a calculator and see what the LCD would be. The smallest number that could be divided by each of these denominators. Okay, so it's not terrible in this case, but my common denominator here, if I were to add these fractions, would be 12. So what I could then do is use 12 as my guess. So I'm actually going to use their guess here because the equation's already complicated enough. Let me just write the function though. So I'm going to say x equals 12. The function was x plus, I think it was 2/3. I'm going to try to do it from memory here. 2/3 x, 1/2 x, and 1/4 x, I think. Moment of truth. Yes, okay, so 12 plus 2/3 of 12, which is 8, plus half of 12, which is 6, plus 1/4 of 12, which is 3. All right, so 29 is what I would get as my result. So my correction ratio is going to be equal to what I should have got, 145, over what I did get, 29. And I get a result of 5. So that means that if I take my guess of 12 and multiply it by the correction factor of 5, I should get 60, and that is the answer. Right? Obviously, the biggest challenge here, I think, assuming that you understand this approach, is getting the equation first from the words. Right? So I'll do the last one here too. The quantity or a quantity plus its double, all right? So the quantity we call x, double it, 2x, its third, 1/3 implied, results in 18. So the plus part allows us to come up with all that stuff on the right. In this case, we could just try 3. All right, so I'm going to guess x equals 3. So x plus 2x plus 1/3 x. So 3 plus 2 times 3 plus 1/3 of 3 gets you clean numbers every step of the way, which gets you a result of 10. My correction factor, what they got, 10. No, 18. Sorry, I was looking at the wrong thing. Well, we got 10. So reduce this down, 9/5. So my answer is going to be what I guessed multiplied by my correction factor, which is going to be 27/5, 27/5 if you want. All right. So this one not quite as clean, but still easily done without the use of a calculator, which is one of the benefits of this sort of calculation. So now you should be good to go for 3.1.1, the exercises here. There's a bunch of them, so good practice.